On va rester dans l'eau douce avec Selina. So thanks, Selina. Selina vient de l'université de Copenhagen. She's working on microplastics in freshwater, and she had brilliant communication last year about reusable plastic containers that you can have. So she will talk a bit about that and about how to detect also these microplastics. Thanks, Selina, for being there. And the floor is yours.
Can you help me to get it started? I don't understand. Oh, yeah, of course. Perfect.
Thank you for the introduction. So my main research focus is the identification of known and especially unknown chemicals in the aquatic environment. So normally I'm investigating wastewater, surface water, or groundwater. But this study we did out of curiosity to see what compounds are migrating out from reusable plastic bottles. A little bit more to the background. Reusable plastic sports bottles are widespread used in different sports like football, in the gym, Tour de France. There you see a lot of these bottles. And so far, these bottles are only analyzed for well-known contaminants. So you see often the bottles labeled as BPA-free, but you don't know if there is maybe another bisphenol S in the bottle. So the bottles we investigated were from a kids' football team. Our group leader is also a football coach, so we got there a lot of bottles from the kids, and they were already complaining about the smell of the bottles. Looking a little bit into the producer side, there I found in the internet that they were writing about these bottles that they are made out of biodegradable polyethylene. They are 100% recycled, and that is achieved by adding a bio-batch. I was writing them and asking what is the bio-batch, but of course they are not allowed to tell me what is in their bio-batch. But this bio-batch apparently has no effect on the use of the bottle until it is in the landfill or is accidentally left behind during a ride through the forest, and then it should decompose into water, humus, and gas. So we were, of course, curious if that is true or if there's not something already leaching out during you use the bottle. A little bit to the background, what are potential sources for chemicals migrating into the drinking water from these plastic bottles? Of course, you have the material itself, what we heard now a lot about, which are intentionally added substances. That can be the plastic itself or additives. But then you also have these non-intentionally added substances. They can be, for example, during the production process be introduced because the bottle is in contact with the machines, or it's just somehow coming into the bottle. And other non-intentionally added substances can be that the material by environmental processes like sunlight are transformed to other products, and also during the production there can be, or there are impurities, or also incomplete process chemicals. So we try to have a more universal method to identify also the unknown chemicals. Even the intentionally added substances, for many, there are no analytical standards available, so it cannot be really screened for these compounds. The experimental setup was as followed. We were buying some new bottles. Then we were using the new bottles, but also bottles from this kid football team, put them in the dishwasher. And as a third step, we were flushing these bottles very thoroughly by putting water in, shaking out, water in again, and that for 10 minutes. Try to get rid of everything from the dishwasher and see what is then migrating into drinking water. Then we stored drinking water for 24 hours after each of these 3 steps in the bottles. We didn't use methanol or anything else. Our aim was to be as close as possible as the real consumer would use it. After that, we were enriching that. Just shortly, it was 1 liter water, what was up concentrated to 1 milliliter extract. By that, we had we needed it to be more sensitive in our analytical method. and then we analyze it with liquid chromatography coupled to high resolution mass spectrometry. To talk too much about this method would be a little bit nerdy, but at least one slide is important to understand how we could, with that method, identify these unknown chemicals. So we use something what we call the chemical fingerprint. That is a chromatogram that you get out for every sample. And you see all of these. Yeah, each of these peaks is one compound. And then there are some of these peaks where we know exactly what it is because we have an analytical standard, so we can quantify these chemicals. Then there are some peaks where we have some libraries, and when we compare it, maybe we see a hit, so somebody reported them before, and then by the pattern, we have a quite high confidence that we know this compound. But then there are also some compounds where we have no hint what it is. We need to prioritize, and yeah, there the detective work starts with our tools to try to identify what can be these unknown chemicals. When we look in this non-target screening approach now at the chromatograms of the water stored in the bottle after these different processes, then we see it here from the new bubbles or bubbles in general. So these are probably peaks which are coming from the plastic. Then after it was in the dishwasher, we see many more of these peaks coming from the soap. But then after additional flushing, we get rid of many peaks, but there are still some remaining. A little bit more systematic shown here. This is a heat map. So what you can see here is each line is one chemical. There are 2,000 lines. And blue means it's not detected, and red means it's detected in a high peak intensity, so probably high concentration. Let's start at the bottom, the new purchased bottles. There we saw some chemicals which are not after the dishwasher in and not after the additional flushing. So there it's blue. So that means that were probably production chemicals which were flushed away easily. But then we can also see some production chemicals which are in after the dishwasher, and after the dishwasher some of them are even red. So that means they are leaching out in even higher concentration. And then there are some which are still in after the dishwasher, but then they are flushed away after additional flushing. The highest amount of chemicals came from the dishwasher soap. Luckily, after flushing your bottle again, they are removed from the bottles, but there are still some dishwasher chemicals which were sticking to this material. Now I will talk a little bit more about compounds we identified in this big bulk of compounds. First to the dishwasher compounds, most were detergents, of course. Here an example of polyoxyethylene lauryl ether, so that are non-ionic surfactants. They have an unpolar tail here and a polar tail. And they occur in homologous series, and that just means that here this ethylene oxide, there can be more group attached. The more of these polar groups are attached, the more polar is the molecule, so more water soluble. Here you see now on the x-axis in this direction with more ethylene oxide groups on a molecule, so that means more polar. That was after the dishwasher. There they were all migrating in similar concentrations into the drinking water. And then after we were flushing the bottle, we could see that the more polar compounds were really gone, but the more unpolar compounds from these detergents were still leaching into the drinking water like before we flushed it. And that's also what you see in this chromatogram when you just look at that these chemicals are removed and these are still sticking. Now to compounds which were migrating from the plastic itself. There we identified some plasticizers, for example polycaprolactone, which are biodegradable polyester for elastic properties. They are normally occurring in polymers, and they will also not migrate into the drinking water. but they can, by incomplete production processes or during the use of this bottle, be degraded into their monomers, and when several monomers are clustering, then this is called oligomers, and we found in different sizes. And there, again, there's no analytical standard available for these kinds of oligomers, so it cannot be tested for toxicity tests or to identify the concentration of these chemicals, so it's unknown what is the health effect. They were detected in a new bottle after the dishwasher, probably because of the high temperature during the process. They were after that migrating in higher concentration into the drinking water, and after additional flushing, less, but they were still there. One very interesting compound was DEET, which is well known as insect repellent, so it's normally used in mosquito sprays. It was in very low peak intensities in the new bottles, but the used bottle we saw quite a high signal for these compounds, and they were not detected in glass bottles, so for the whole experience we always had glass bottles as comparison or as reference, running the same experiments, and there we couldn't find any of these chemicals. So now it's the question, where does this DEET come from? It's already, when you read on the mosquito spray written, if you wear a watch with an armrest, be careful because it can affect the material. So it seems that it has some plasticizer effects, and we were also searching a long time into literature, and finally we found one publication which is writing about DEET can be used as plasticizer. We could see that laurolactam, a plasticizer, was also detected in the water, and it was following a similar trend. So when laurolactam was high, also DEET was high, and also the sum formula is very similar. So we assume either DEET is introduced as plasticizer itself, or it's just formed as a transformation product from other chemicals. Another group of identified compounds were slip agents, which are fatty amides. They migrate or bloom to the surface where they form a microcrystalline structure that decreases friction. That's used in the production process. It's like when you're baking and you have your baking form and try to get your cake out. That's the same what they are doing with bottles. So it makes sense that we found a lot of them in the new bottles, and the signal was much lower after flushing these bottles, so that just shows that it is important to wash your bottle before you use it the first time, but maybe not in the dishwasher. With this non-target approach, there are of course many chemicals what we cannot identify what exactly they are. So we had a focus on these three masses because it were the highest peaks we found in the chromatogram. They were coming mostly in the new bottles, but they were still in quite high peak intensity and after the dishwashing, after additional flushing. We came so far that we had an idea about 3 suggested structures, how they could look like, but we couldn't find anything in literature about something with the sum formula. So these compounds are not known yet, and so we also don't know if it's maybe transformation products from antioxidants that would fit to this first structure, or from slip agents, because there are also these amides, or if they are introduced during the production process by something completely different. Now it's of course interesting to know if it's toxic what we detected, and that I cannot answer. So we identified 42 chemicals. For most of them, there are no toxicity data available because of the lack of analytical standards. I made an estimation by so-called grammar rules. So there you're looking at the structure of the chemicals, and by that you can estimate the toxicity. And only for some chemicals, which is then in dark red, I found something in literature that they are toxic. Yeah, most of the compounds which we've detected and were toxic were related to the group of photoinitiators, because they are already well known for endocrine disrupting effects or carcinogenic effects. When we were looking at the bottles and just building a sum of the toxicity and peak intensity, then it was like the used bottle, which was red, after the dishwasher process had the highest toxicity, and after flushing the toxicity is always decreasing. That's for the other bottle the same, and that's the new bottle after the dishwasher and after flushing. Yeah, it's of course also, first of all, there are no toxicity data, and the concentration is also a challenge, because when we don't have an analytical standard, you can normally not determine it. We are now working on a strategy that we can get the concentration out. Just as a summary again, what we saw were the different compounds migrating from the plastic itself, like plasticizers, slip agent, and photoinitiators. The surfactants were coming from the dishwasher soap, and altogether was then migrating into the drinking water. As a conclusion, we tried to show in our study that under real consumer use, what it can migrate here, and we found thousands of compounds where we are far away from identifying all. Here we identified 42 contaminants, and that raises, of course, the questions: is plastic suitable for reuse, especially when they are labeled as biodegradable? And the risk of using the bottle is unknown at this current stage, like I just explained. We also have an ongoing work. It's a master's student, and she's very motivated, so she tries now to look in all these bottles. Let's see how far she will come. Yes, but we also published it, and thank you for listening. I think in English and French questions, okay? If you translate.
Questions?
Thank you very much. I'm not sure to understand why this repellent, diethyltoluamide, can appear in those bottles. You explained that it could be a subproduct of the degradation of the plastic, but if it's not the case, how come this DEET can arrive here in this? If it's a repellent initially, how come this repellent can reach the bottle?
So it is, I think, as insect repellent, it's probably used because of the smell or something what mosquitoes don't like. I don't know why it's used there. So of course it could be as an impurity it's in, but then it doesn't make sense that it was so systematically found really in the plastic bottles and not, for example, in the glass bottles. It's just the structure, which is apparently good for a plasticizer. Sometimes it can just be that a chemical can have two completely different use or pattern because with the chemical structure, I think.
Maybe just to add to that, I mean, because there are so many chemicals out there, and people tend to, use what's cheapest, what's, available on the market, what serves their function. Maybe it even is being intentionally used and someone doesn't realize that it's actually got these biocidal properties. It's quite likely. But I think it's also very compelling, this hypothesis that it's a degradation or transformation product. So.
It's also DEET is in the wastewater, for example. It's the whole year at the same level detected in wastewater effluent. So it doesn't make sense. It's only used as insect repellent. There is another source somewhere where we use it and we don't know where we use it.
Have you contacted the company that is making these biodegradable bottles, and if they know that the DET was used as a plasticizer, or If it
No.
was a NIAS or
Of course,
IAS?
we could do it. The first time they were not so so happy to talk with us. Often these bottles are bought by other companies, like sports companies, and they do then their brand on it. So sports company were then writing us and wanted that we investigate more of these bottles, and they were then the middle contact to the manufacturer. But then also the manufacturer, often they just get their parts from somewhere else and they don't know what is in everything they get from different, yeah.
I had,
Thanks a lot for your very nice talk. I have a lot of questions, but maybe I can ask two questions. Do you have an idea of the concentration of these substances in water? Because you use high resolutions mass spectrometry, and it means maybe you have a picogram per liter range, or maybe less. Do you have?
Yeah. So the high resolution mass spectrometry is of course less sensitive than a triple coat, for example. So we would detect higher concentration, but we up concentrate 1,000 times. So my rough guess is that we are in the nanogram per liter range, but I haven't investigated that for this study.
If it's a nanogram per liter, it's huge. I think
It
so.
would be, yeah, of course, depending on the compound, yeah.
Yeah. And my second question, you speak about migration, and migration means that you have a stock of this pollutant inside the plastic or the bottle. Do you have any assessment of this store of pollutants in plastic to know at which scale the migration can end up?
No, we didn't study that. It could be interesting.
In general, when you have packaging such as reusable packaging, you have some regulation, of course, connected to this food packaging. And do you think that every packaging you test follow this regulation? Or because it's strange, when you have a reusable material, you need to proceed to a 3 cycle of migration before
Yeah, but that's shown by the study. They know specific kind of chemicals.
Yeah.
They do the target method. They are not in, no BPA, that's fine. But they just replaced it by other compounds what are not regulated, and then it
So
starts
for
the
you,
problem.
it's especially connected to NIAS?
Sorry?
So non-intentionally aided substances, especially connected to these non-intentionally aided substances?
Yes.
Okay.
But also intentionally added substances. There are so many out there. I think Jane knows that better. But yeah, which are not regulated, where no standards are available.
Yeah, I think a general comment about that is that we don't know exact composition of all the containers, either plastics or cellulose made of paper and plastics. I had a question regarding the new studies that you are doing. Is there any stainless steel bottles?
Oh yeah, so not in this, but this is really just a master project, but we try now to apply for funding in there, of course, stainless steel. Yeah. Because there it's of course interesting also to investigate for heavy metals in a little bit more.
Because I think we have a lot, at least in France, we find a lot of inox, so stainless steel bottles with a slight
Coatings.
plastic joint,
yeah.
you know,
Yeah.
but we have also the question about this migration, or perhaps is there an inner lineage of the bottle? We would be interested in looking into that, but yeah, it's striking the number of compounds.
Maybe I have one last question. Do you have any control of the air contamination? Because if you have a bottle, if you open, for example, 20 seconds your bottle.
When what?
if you open your bottle, only
Yeah.
20 seconds, and you close down, and you analyze then. Do you have any control about the air pollution? Because I think maybe, or I'm not sure, that some of substances that you detect coming from the atmosphere.
So yes, we had many controls. We had the glass bottles, which we are always open the same time. I think there can be many impurities also, in the lab, but I think from the air that are very volatile compounds, and with the liquid chromatography, of course, could still happen, but we had many controls with bottles. What we were then, of course, it can always also come from the water, so it was very important to have the controls to subtract what we find in the controls.
Last question for me. Can you investigate also the microplastics or nanoplastics? Because here you talk about the substances, molecules, but do you have...
In our working group, we started now also with this pyrolysis GC for other purposes, but we could do it now. Not me, but our working group, yes.
With an amount like 500 milliliters, it's sufficient?
We don't know yet, or I don't know, but they are not so far yet that they have real samples. But could you do that?
It's a question too.
Okay. Okay.
Okay, no more questions. Okay, thanks a lot, Selina.
Thank you.
So, now it's my pleasure to introduce Jane Mung, that is working at the Food Packaging Forum in Switzerland. We met, I think, more than 10 years ago at the Gordon Research Conference on the crime disruption. But so since this moment, she is working with glass and to also show that you have multiple things that we don't know about the polymers. And so she will talk today about the food containers and the chemicals that are in the contact of food. We will have a follow-up discussion tomorrow morning with that. And Jane is going to present also tomorrow morning the Plastique project. It was supposed to be Liza